I mean, are we just made of these tiny little solid particles, or could it be something, I don't know, more fluid, more wave-like? Today, we're doing a deep dive into an idea that really stretches the mind. It connects established quantum mechanics with some pretty bold, maybe even speculative theories about reality itself. We're looking primarily at an analysis called The Universe is a Symphony of Standing Waves. It explores this very idea. And our mission today is to unpack how waves, became so central to physics in the first place. Then we'll look at where the sort of mainstream path diverge and explore this really ambitious alternative theory, the wave structure of matter, that tries to unify absolutely everything using waves. Get ready for, hopefully, some aha moments and maybe some surprising facts about the very fabric of existence. Okay, let's dig in. So our story really starts around the turn of the 20th century. Classical physics, Newton and Maxwell was incredibly successful, but it started hitting roadblocks. Things like black body radiation, why hot things glow the way they do. They had this problem called the ultraviolet catastrophe, and also the photoelectric effect, light hitting metal and knocking electrons off. Classical ideas just couldn't explain these observations properly.
No, they couldn't. And it's really fascinating how these seemingly niche experimental problems ended up completely revolutionizing everything. Max Planck, trying to solve the black body problem, made this, well, radical leap. He suggested energy wasn't continuous, but came in these discrete packets, or quanta. The energy was proportional to frequency, E equals h nu. That was the start. Then Einstein took it further. He proposed that light itself is made of these quanta, what we now call photons. And bam, that explained the photoelectric effect perfectly. So suddenly, light, which everyone knew was a wave, also had these undeniable particle-like properties. Wave-particle duality for light was born.
Okay, so light, a wave, can act like a particle.
Yeah.
And naturally is the next question, right? Louis de Broglie, in 1924, he had this incredibly bold idea about symmetry. He basically said, well, if waves can be particles, why can't particles be waves? He even gave us an equation. Wavelength equals Planck's constant divided by momentum, LOP. Now, for everyday objects like, I don't know, a baseball, this wavelength is ridiculously small. You'd never notice it.
Absolutely tiny, yeah.
Undetectable. Oh, but for something as small as an electron, suddenly that wavelength matters a lot.
It becomes crucial. And this wasn't just, a neat thought experiment. It was a prediction. And incredibly, it was confirmed experimentally really quickly. Just 3 years later, 1927, Davison and Germer, they shot electrons at a nickel crystal and saw diffraction patterns, exactly like you'd expect from waves.
It's like X-rays diffracting, right?
Precisely. And then there's the quintessential example, the double-slit experiment. You fire electrons, even just one electron at a time, towards two slits, and what you see on the screen behind isn't two clumps, like you'd expect for particles. You see an interference pattern, stripes. That's classic wave behavior.
Which raises this huge question, doesn't it? If a single electron can interfere with itself, what does that even mean about its nature? How is it going through both slits?
Exactly. It implies the electron isn't a tiny point particle before it hits the screen. It has to be something more spread out, something wave-like to create that pattern.
So how did physicists start to describe this mathematically? If it's a wave, there must be a wave equation.
And there is. Erwin Schrödinger, in 1926, came up with his famous wave equation. You often see it as Hey. This equation governs the behavior of the wave function, that Greek letter psi. Psi basically contains all the information about the quantum state of the system, like the electron. It's the mathematical description of this matter wave.
Okay, the wave function. The math works. But what is it, physically? Is the electron really smeared out like a wave described by psi?
Now that was the million-dollar question. And there was a huge debate. Schrödinger himself, initially, he thought psi represented a physical wave. Like, the electron's charge was literally smeared out in space, according to psi. But that interpretation had problems, because whenever you actually look for an electron, you detect it at a single point. It's never found smeared out.
Right, the measurement collapses it, sort of.
Well, that's one way to think about it. The interpretation that won out and became the foundation of standard quantum mechanics came from Max Born, also in 1926. Born proposed that psi itself isn't the physical wave. Instead, the square of its magnitude, written as emitted, tells you the probability of finding the particle at a particular location if you were to measure it.
Probabilities. So the wave function isn't the electron, it's a map of where the electron might be found.
Exactly. It's a probability amplitude. The math uses waves, absolutely, but the dominant interpretation, the Copenhagen interpretation, stepped back from saying the particle is a physical wave. It describes its potential behavior using wave mathematics.
That feels like a really crucial split then. using the math of waves, but abandoning the idea of a physical wave being the fundamental thing.
It was a crucial schism, yes. Mainstream quantum mechanics embraced the probabilistic view, which works incredibly well for predictions, but it left some, like Einstein, feeling philosophically unsatisfied.
Because it leaves this weirdness, right? How do you get stable atoms, definite structures, if everything's just probabilities governed by waves?
Well, that's where the concept of the electron as a confined wave becomes incredibly powerful. Think about standing waves.
Like a guitar string. You pluck it, and it vibrates at specific frequencies, the harmonics. Those stable patterns or standing waves. Anything else just kind of fizzles out.
Exactly. And that's not just an analogy for an electron in an atom. It's pretty much the core principle. The electron is trapped, confined by the electric pull of the nucleus. Because it has wave properties, it can only exist in states where its wave pattern fits stably within that confinement. It has to form a three-dimensional standing wave.
So it has to interfere constructively with itself. Like the wave pattern has to loop back and match up perfectly.
Precisely. The condition is essentially that the path length of the electron's wave around the nucleus must be an integer multiple of its de Broglie wavelength. 2 par equals nah, basically. Only certain wavelengths, and therefore certain energies, allow for these stable standing waves. This naturally explains why electron energy levels in atoms are quantized. They come in discrete steps. It's not arbitrary, it's a direct consequence of wave confinement.
Wow. So quantization just pops out naturally from the wave picture. It's not some extra rule you have to add.
Exactly. And those shapes we learn in chemistry, the SPDF orbitals, those aren't just random blobs. They are visual representations of the probability distributions, the emitted, for these allowed 3D standing waves.
Like the different ways a drum skin can vibrate with nodes and antinodes.
That's a great analogy. The s orbital is like the fundamental vibration spherical. The p orbitals have lobes and a nodal plane through the nucleus where the probability of finding the electron is 0. The d and f orbitals have even more complex shapes, more nodes and antinodes.
And this standing wave idea doesn't just stop at single atoms, does it? It explains how they bond together.
Absolutely. It's fundamental to chemistry through molecular orbital theory. When atoms come together, their atomic orbitals, these standing electron waves, overlap. If they overlap in phase, their wave functions add up constructively. This creates a lower energy bonding molecular orbital, where electron probability density increases between the nuclei, pulling them together. That's your sigma bond or pi bond.
Okay, constructive interference holds them together. What about destructive?
If they overlap out of phase, they interfere destructively. This creates a higher energy anti-bonding molecular orbital, often with a node right between the nuclei, pushing them apart or weakening the bond.
It's really quite amazing how this model of electrons as confined standing waves explains so much the stability of atoms, the shapes of molecules, chemical bonding, the properties of matter.
Its success is extraordinary. It underpins basically all of modern chemistry and materials science.
Which leads to a really profound question, doesn't it? If the arrangement of particles, like electrons in atoms and molecules, is so perfectly described by standing waves, could the particles themselves be standing waves at an even more fundamental level?
That's the leap that takes us beyond standard quantum mechanics.
And that brings us neatly to the wave structure of matter, or WSM. Now, this is definitely more speculative territory, but it's a compelling idea. It basically takes that standing wave concept we just discussed
and generalizes it hugely.
Right. It proposes that not just electron arrangements, but everything, all particles, all forces, maybe reality itself, are just manifestations of waves in one single underlying medium.
Yeah, the core idea, especially in models like Milo Wolf's space resonance theory, is that an elementary particle, say an electron, isn't a point at all. It's pictured as a spherical standing wave. Imagine waves converging inwards from all of space, the in wave meeting at a center, and then diverging back out the out wave. The particle feeling we get is associated with that high-density wave center.
So the particle is the wave structure.
Essentially, yes. Its stability comes from a resonant condition between the in and out waves. They have to be phase-locked. And importantly, these waves extend outwards indefinitely, their amplitude dropping off as 1 over the distance, r. This one behavior is proposed as the origin of long-range forces like electromagnetism.
And this implies space isn't empty then. It's the medium for these waves.
That's a crucial postulate of WSM. It rejects the idea of an empty vacuum. Instead, space itself is the physical wave medium. It's active, not passive. Its properties, like its density, are determined by the superposition of waves from all other particles in the universe. It connects back to Mach's principle, the idea that local physics depends on the large-scale structure of the universe.
That sounds very different from quantum field theory, which talks about multiple fields and virtual particles popping in and out of the vacuum.
Very different. QFT has a sea of different quantum fields, one for each particle type, plus virtual particles mediating forces. WSM proposes just one single, real, physical medium space itself, and everything emerges from wave interactions within it.
I've seen some visualizations. People like Gabriel Lafreniere have done amazing work showing these spherical waves interacting. How does WSM explain a moving particles wave, the de Broglie wave?
Right, those visualizations are helpful. WSM explains the de Broglie wave as the Doppler effect. As the wave center moves through the space medium, the incoming and outgoing spherical waves experience frequency shifts, higher frequency in front, lower behind. The interference between these Doppler-shifted waves creates the beat frequency that matches the de Broglie wavelength.
And there are variations on this theme, right? Like the ball of light model or energy wave theory?
Yes, they're related concepts, all centered on particles being stable, localized wave structures rather than point-like objects. The details differ, but the core idea is similar.
Okay, so the big appeal of WSM is its claim to derive fundamental properties, not just assume them. Let's break that down. How does it explain, say, mass?
In WSM, mass isn't something a particle has intrinsically. It is the energy contained within the localized standing wave structure. It comes directly from Einstein's Einstein, or perhaps better. The energy is proportional to the frequency of the standing wave resonance. More energy trapped in the wave center means more inertia, more mass.
Okay, mass is wave energy. What about charge?
Charge is seen as emerging from how the waves interact, specifically the phase relationship between the spherical waves of different particles. If two particles' waves are in phase where they overlap, they interfere constructively, leading to repulsion like charges repel. If they're out of phase, they interfere destructively, reducing the total wave amplitude, which leads to attraction unlike charges attract. The sign of the charge, plus or mech, reflects this phase relationship.
Let's spin, that weird quantum property.
WSM offers a surprisingly physical picture for spin. It's proposed to be a kind of spherical rotation right at the wave center, necessary for the in wave to smoothly transform into the out wave while maintaining the resonance. The math of this spherical rotation naturally leads to the requirement of a 720-degree turn to return to the original state for spin 12 particles like electrons, explaining that strange property geometrically.
That's definitely more intuitive than just calling it an intrinsic quantum number. So what about forces? If charge is about wave phase, how do forces actually work without force carrier particles like photons?
This is another radical departure. WSM proposes no force carriers. Instead, forces arise from something called the minimum amplitude principle, or MAP.
MAP.
Minimum amplitude principle. The idea is that wave centers naturally move towards locations where the total wave amplitude from all surrounding particles is minimized.
So things just settle into the quietest spots in the wave pool.
Sort of, yes. For the electromagnetic force, as we said, constructive interference between charges increases amplitude, so they move apart, repulsion, to minimize it. Destructive interference between unlike charges decreases amplitude, so they move closer, attraction, to minimize it further. And gravity, that's viewed as a secondary, much weaker effect. The idea is that the presence of matter waves slightly increases the density of the underlying space medium. This slightly slows down the waves traveling through it. Other particles, following the MAP principle or simply seeking regions where wave velocity is higher, which relates to frequency and energy, will tend to drift towards these denser regions. That drift is gravity. No graviton needed.
It's an incredibly unified picture. One medium, one kind of wave, deriving mass, charge, spin, forces. How does it handle the weirder quantum stuff like entanglement?
Well, WSM proponents argue it handles them more naturally. Take entanglement, that spooky action at a distance. In WSM, it's not spooky because particles aren't truly separate. Their spherical wave structures extend infinitely, and crucially, their in-waves originate from the waves of all other matter in the universe, that Machian connection again. So, particles formed in the same event share common in-wave origins. Their structures are inherently correlated from the start because they're part of the same interconnected wave system.
So measuring one instantly affects the shared wave structure, influencing the other.
Effectively, yes, but the influence propagates via the waves at the speed of light, consistent with relativity. There's no faster-than-light signaling, just inherent correlation.
Wave-particle duality.
WSM says there is no duality, fundamentally. There are only waves. The particle aspect is just what we perceive or measure at the high-energy wave center. The wave aspect is the extended structure. What you observe depends entirely on how you interact with it, what kind of experiment you do.
And quantization.
That falls out naturally from resonance, just like in the atom. Only specific frequencies can form stable, standing waves, whether it's an electron in an atom or the fundamental structure of the particle itself. Discrete energy levels are just the allowed resonant frequencies.
So philosophically, it's a huge shift. The standard model seems more kinematic, like particles moving on a stage. WSM sounds dynamic, with space itself being an active player in constant dialogue with matter.
That's a good way to put it. It's a holistic, interconnected view where everything arises from the properties of this single wave medium.
Okay, but let's contrast this with a champion, the reigning theory, the standard model of particle physics. It's the framework that physicists actually use every day. It describes, what, 3 of the 4 forces? Electromagnetism, the weak and strong nuclear forces. And it catalogs all the known elementary particles. You've got the 12 fermions, quarks, and leptons in 3 generations making up matter. Then you have the bosons mediating forces, photons, gluons, W and Z bosons, and of course the famous Higgs boson, giving particles mass via the Higgs field.
Right. And the mathematical language underlying the standard model is quantum field theory, QFT. In QFT, the fundamental things aren't particles, but fields that fill all of spacetime. There's an electron field, a quark field, a photon field, and so on. Particles, like an electron, are viewed as localized excitations or quantized vibrations of their respective fields. And we have to emphasize, the standard model built on QFT has been monumentally successful. Its predictions have been tested and confirmed in countless experiments, often to incredible levels of precision. It's arguably the most successful scientific theory we've ever had.
No question, its track record is amazing. But, as we mentioned, it has known limitations. It doesn't include gravity. It doesn't explain dark matter or dark energy, which seem to make up most of the universe. It also has something like 19 arbitrary constants numbers, like particle masses or force strengths that just have to be measured and plugged in. The theory doesn't explain why they have those values and why 3 generations of particles. The standard model is silent on that.
Exactly. These are the big open questions driving the search for physics beyond the standard model. Many physicists expect it to be an effective theory, a low-energy approximation of something deeper.
So let's put WSM and the standard model side by side. The differences seem pretty stark.
They really are, right down to the foundations. Fundamental entity. SM has multiple quantized fields. WSM has one continuous wave medium space, particles. SM sees point-like excitations. WSM sees extended wave centers, mass. SM uses the Higgs mechanism. WSM uses resonant wave energy, charge. Intrinsic property in SM, emergent from wave phase in WSM spin, intrinsic quantum number in SM, physical rotation in WSM, forces, exchange of virtual bosons in SM, wave centers minimizing amplitude, MAT, in WSM, vacuum, a dynamic sea of virtual particles in SM, the physical medium itself in WSM, and math. Complex gauge theory for SM, simpler real scalar waves for WSM.
That ontological parsimony of WSM deriving everything from one substance is definitely appealing. It sounds simpler, more elegant.
It does, conceptually.
But elegance isn't enough in physics, right? The big hurdle must be whether WSM can actually reproduce all the successful predictions of the standard model quantitatively.
And that's precisely the main criticism from the mainstream perspective. WSM is largely retrodictive. It offers qualitative explanations for things we already know, but it hasn't really produced unique, quantitatively precise, testable predictions that differ from the standard model and could be experimentally verified.
It hasn't predicted a new particle or effect that's been found.
Not in a way that's gained widespread acceptance or couldn't also be accommodated within extensions of the standard model. Another major issue is the mathematical framework. That simple scalar wave equation WSM often uses is generally considered insufficient to describe the full complexity of observed reality. You need the more complex math of QFT spinors for spin 12 particles, vector fields for spin 1 bosons, group theory to handle symmetries to match experimental results. WSM hasn't convincingly shown it can derive all of that structure from its simpler starting point.
So it struggles with the mathematical rigor needed.
That's the view. It also rejects core QFT concepts like multiple fields, virtual particles, and renormalization, the technique used to handle infinities in QFT calculations. While renormalization is admittedly mathematically tricky, QFT provides an incredibly powerful and predictive computational framework that WSM currently lacks a comparable alternative for. And finally, there's the argument that WSM is essentially revisiting an ontology, the idea of particles as literal physical waves that was considered and largely abandoned by the founders of quantum mechanics, because the probabilistic interpretation based on arggen proved far more robust and successful in explaining experiments.
Although WSM proponents would fire back, right? They'd say the standard model is too complex, too patched together with all its parameters, relies on unphysical point particles needing renormalization, and that its probabilistic nature is a philosophical cop-out.
Oh, absolutely. It's a fundamental disagreement about what constitutes a good or complete physical theory. WSM prioritizes ontological simplicity and intuitive physical mechanisms. The standard model prioritizes mathematical consistency and quantitative predictive power, even if the underlying reality it describes is less intuitive.
So wrapping this up for you listening, that core idea, the electron behaving like a confined standing wave in an atom, that's solid. It's baked into quantum mechanics. It's the foundation of chemistry. It beautifully explains why atoms are stable and why they have discrete energy levels.
It's incredibly successful and profound, and yes, that very success inspired the grander vision of the wave structure of matter trying to build the entire universe from waves. But as we've discussed, WSM faces major challenges. It hasn't yet demonstrated the quantitative predictive power to match, let alone surpass, the standard model. Its mathematical underpinnings are viewed as insufficient by most physicists, and it requires rejecting the framework of quantum field theory, which, despite its own conceptual puzzles, remains extraordinarily successful experimentally.
So you might say a beautiful, elegant idea isn't automatically a correct one. Science demands that quantitative rigor and experimental validation.
Precisely. Conceptual elegance is attractive, but it has to deliver the numbers.
So while it's tempting and maybe even poetically satisfying to think of the universe as a symphony of waves, the most accurate, most predictive description we currently have of that symphony is still the standard model and quantum field theory, complexities and all.
Which leaves us with a final thought, perhaps. WSM is currently outside the mainstream. What would it actually take for a radically different, perhaps simpler, theory like this to truly challenge and potentially replace an established behemoth like the standard model? What kind of decisive new evidence or theoretical breakthrough would be needed to make the physics community reconsider such fundamental assumptions about reality?